Polaris, the North Star, has guided navigators for centuries, but what it does in the sky today reveals something far more powerful, a way to test the shape of the Earth, because the way Polaris behaves, it works perfectly on a globe, and completely breaks the Flat Earth map. I already made a short video showing this, so instead of setting everything up again, here's the clip that I had posted on TikTok. It was filmed vertically, but I'm just going to post it here.
But I have a little globe here, a protractor, and both of them tied up at the same point on that gazebo. So people don't understand how finding Polaris and celestial navigation works on a globe. And it only works on a globe because if we're on the North Pole, Polaris is at 90. And then as we travel down the globe, it's weird that we get an angle to Polaris way out there. But people think that this works on a flat surface. It doesn't. And then as we get to the equator, it's zero. It's just below zero because I don't have Polaris at infinity from here. But yeah, it's weird. So it's weird how as we go up the globe, our angle to Polaris changes exactly like we would expect on a globe.
So as you saw here, on a globe, Polaris is directly overhead at the North Pole. That's 90 degrees straight up. At the 45-degree north mark, about halfway around the distance between the North Pole and the equator, is right at 45 degrees. And then as we hit the equator, it's pretty much at zero. This isn't the perfect scale, but you could make sense of it. Those angles exactly match your latitude, and that's spherical geometry in action. So I'm using the Gleason's map because it's the best we have. No other flat earther has presented a map. In the flat earth lack of model, Polaris is usually placed directly above the North Pole in the center of the map. So theoretically, everyone should be able to see Polaris just at different angles. But in reality, Polaris completely disappears once you've entered the southern hemisphere. On a flat surface, that shouldn't and wouldn't happen. Even at the farthest edges, it should still be visible, just low in the sky. Now I'm going to show you another video I made for TikTok. This one is testing with a large flat earth map printout that I had made. Again, it's vertical format, so I'm just throwing it in here, but I already did it and didn't want to refilm everything. Here's how it works.
So here we've got the 4-foot printout of section of the Gleason map. I used North America, South America because most people are watching in America and parts of Canada. On this one, we've got the equator, Tropic of Capricorn, Tropic of Cancer. They even have the Bermuda Triangle on there. So this pin here is measured about 3,000 miles out. I just measured North Pole to Quebec and then went up. So if we're close to the North Pole, it kind of works, but as we move away, the angle drops. And so at New York, at Polaris at 3,000 miles, New York is at 36 degrees. When we come all the way out to the equator is only at 23 degrees, which it should be at zero, not 23 degrees. With Polaris at 3,000 miles, Santiago is at about 21 degrees. So here, as we can see, this is our 45-degree parallel. I put a pin in there, so it lines up pretty much 45 degrees here. And as we move out, we'll go New York, gets to about 42, 43 degrees. Shoot, the equator's only at 30 degrees. When 45 degrees to Polaris works, the equator doesn't work because it's at 29, 30 degrees. So now we can put Polaris even higher and move it out, and again, we have the same issue where the drop does not work. So here we've got the equator 43, 44 degrees. So now let's try to get it to work with Polaris at, I don't know, 500 miles above the surface. So New York is now 10 degrees from Polaris. The equator is now 8.5 degrees from Polaris, and Santiago, Chile is what, 6 or 7 degrees from Polaris.
So as you can see, no matter where we put the elevation of Polaris on the Gleason's map or any flat map, it just doesn't work out. We can get the elevation correct for one latitude line, but the second we move away from that latitude line, it all starts to fall apart. In real life, observers below the equator don't see Polaris at all. That's not a distance issue, it's a geometry issue. Now I've got two videos to show you. This first one here, this is Polaris being filmed from my location in the northern hemisphere. You can see the stars rotating around it in a counterclockwise rotation, just like we'd expect. Now in this second video, turn my camera around, I'm at 33 degrees north latitude, and look at this, the stars are still arcing across the sky, but they curve downward and to the right. That's the start of the southern sky's rotation becoming visible. The farther we go down south, the more that's going to become a circle around a central point of rotation. That's literally something that cannot happen on a flat plane with a dome overhead. Now, the really important part here is this didn't require anything other than a camera and some clear skies. Anyone can do this. This is the kind of stuff that you yourself can record. No need to rely on NASA or planetariums. Just pick a clear night and look up. Now, here's a fun bonus fact. Flat earthers love to say, the stars never change position, but that's just not true, and we know that. Here's a book from 1865 called Navigation and Nautical Astronomy by Coffin. Now, if we head down to page 119, we can look right here and say, in the case of Ursa Minoris, Polaris, whose polar distance is 1 degree and 25 minutes. So from the center of the polar rotation, it is 1 degree and 25 minutes. Now I'm just going to use the Wikipedia here, but if we look at the declination, we can see that it's 89 degrees, 15 minutes. So off of 40, that's about 45 minutes off of center of rotation. So it's been drifting slowly, predictably, and measurably closer to the center of rotation. That slow shift is called axial precession, and it's something navigators, sailors, and astronomers have been tracking for hundreds of years. Like the navigators that use the position of Polaris being 1 degree 25 minutes off of center while navigating in the 1800s. So on a globe, this all seems to work beautifully. Polaris drops lower as you go south. It vanishes when you reach the equator, and it comes back up when you go north again. You don't lose it because you're too far away. You lose it because you're standing on a curved surface and it's getting in the way. Even Polaris's motion over time, that slow crawl across the sky, it's built into the globe model. Flat Earth model has no explanation for it at all, or just denies it. So can Flat Earth explain Polaris? The answer is in the angles, the sky, and even history books. From geometry to observations to centuries of data, the globe just works. If you hear anything that you're like, that sounds a little off, test it. Test the claim yourself. If you liked the video, please leave a like. If you didn't, a dislike. Let me know in the comments how I'm doing. If there's anything you want to see debunked or anything that you're like, this is undebunkable, by all means, leave it in there and I'll give it a shot. Thank you and have a good one.